Hello guys, and welcome to the tutorial of schematic preparation in XSchem and using the GF18 MCU PDK in the process of schematic creation for Chipathon 2025 digital building blocks, and this is Raditya from team VoidWalkers. And here I'll explain to you how to create a schematic in XSchem before we begin some layout. So before we begin to the technical details on how to use XSchem, it might be good to refresh what we know about the CMOS process and the basic of logic gates when we construct it using a transistor. So here, as you can see in this book, the book title is CMOS VLSI Design, a Circuit and System Perspective by David Money Harris and Neil Weste. And so looking at the table of contents and going to the page 9, and you will see the details of how typically a logic gate is constructed using the simplest gate that you can construct, which is the inverter. And let's take a look at the typical inverter. Here in figure 111, you can see how an inverter is constructed with a pair of CMOS field effect transistor. It consists of PMOS and NMOS. The PMOS act as a pull up and the NMOS act as a pull down. And so this is generally how you construct the logic gate out of a CMOS transistor. I mean, in fact, if you look at the figure 114, this is how the general block diagram of all of your logic gates. All the logic gates have a PMOS for pull-up network and NMOS as pull-down network, which is triggered by the input. And the PMOS source is connected to the supply voltage, and the NMOS source is connected to the ground. Both transistor drain pin will act as the output of the gate. So the output of the logic gate, yes, gate. The transistor gates act as an input, and here we can have the high impedance input, which doesn't require much current to drive, and the output can be low resistance, which is good because we want the output to be able to drive many logic gates down the line, which we usually call fan out. And so there's not really much detail that you have to understand other than the quite important principle that do not leave any net to be floating. It must be tied to either supply or close to supply voltage or close to ground, and that's the basic of the digital design of CMOS. And with that being said, let's see how we can construct the inverter at the using XSchem and ASIC multi-tool Docker container that is applied for the Chipathon. let's see. Okay, so here we have our XSchem already running, but just in case you don't know how to start it, after you start your container, you can just run the terminal. Like here I'm using the VNC version of the Docker container that is applied for the Chipathon, and let's open another terminal and just type XSchem. So there you go, you already have that open, and we just opened a new window of the XSchem. Let's see if I'm recording. Yes, still recording. So that's how you open your XSchem, and the welcome screen. The welcome screen isn't particularly interesting at the first glance, but as you may see here, how to zoom. Okay, so to zoom, you have to use scroll, or the two-finger track if you use a touchpad. And as you can see here, there is a pre-made test bench for various test case scenario. Here we have the ones for the MOSFET, this for the capacitor, this for the bipolar junction, this is for the diode, this is a polysilicon resistor, and also the end well. And after this, you have to create a new schematic. How do we create a new schematic? So let's use the old ones I have created, because I have created the circuit here. It will be handy later for our demonstration purposes and speed up something. So how do we create new circuit? So if you see the toolbar, there's a plus sign on top of here, the rightmost of the schematic tabs, and you click on that, and you have a new schematic. It is blank in particular. And so how can we add some transistor? To add some transistor, you can choose the insert symbol menu here. I'm pointing using my cursor. Click on that, and you'll see the choose symbol window. Click on the FOSS-PDCase GF1ATM CUD libs.tech XSchem. This is the directory where the PDK specific symbols are stored, and you want to use that because that is your transistor, and you will use their definition, their model of transistor. Click on the directory, click on the symbols, and there is a variety of device that you can use. This is called primitives, and we'll choose your NFET and PFET based on the voltage rating that you're aiming to achieve. And here, suppose that we will create a 3.3 logic gate. We'll use the 3.3 volt rated NFET and PFET respectively. So select that, and there you go, the device has been selected, and you can place it wherever you want. So place it here as a low side transistor, and the PFET as the high side transistor. Choose that, and there you go. And then we have to connect these two transistor using wires. How do we connect the these transistors, or basically any device that you have here? We have wires, and to do that, just press W, and then you have wires. Drag the wires to the pins that you want to connect, and click, and there you go. The gates of these transistor pairs are now connected, and these serve as our input. So let's drag some more wires, so it will be convenient for us to make connections. And drag some wires here. Here will be our output. And then drag some wires, And by the way, there is some differences in how your real world MOSFETs compared to these model MOSFETs. So these model MOSFETs have these model MOSFET have 4 pins: your regular source, drain, and gate, and one additional pin named bulk. The bulk pins, this pin will act as your end well, like the body of your. The body is not a good. Body is not an appropriate term to use. Bulk. It is the bulk of your transistor. It is like the substrate of your transistor. And typically, the bulk of the PFET will be connected to the supply voltage. So we just have to connect it to the source pin. And in NFET, the bulk is connected to the ground. So just connect it also to the source pin, which then connect to the ground. There you go. The connection are now complete, and now as a means to connect the circuit to the outside world, we need the device called pins. So open up the insert symbol menu, and wait a minute, and choose the uppermost directory here. It is called the XSchem _library/device, and just search for the device name iPin, OPin, or IO pin, or you can just look it up using the search bar in the bottom of the dialog. So iPin, that's it, we have it. This will serve as our input, and then we insert some more symbols. Now it is OPin. This will be our output. This will be our output, and there is IO pin. This will be our connection for the power. Just copy. To make things clearer and to distinguish between nets, we can double click on each pin and change its names, labeled lab over here, and you type whatever names you want to give. Let's give the name in, good, and then out, double click. This will be VCC, and it will be ground, GND. Okay, and that's it. Our base circuit is now complete. This is our inverter. After this, we will construct our test bench to test our inverter. But before we create our test bench, it is a good practice to export your circuit as a symbol. So your test bench will have like a simpler look, not get bogged down with so many devices that is present in your schematic. Right now there's only two devices here, the PFET and NFET, but as you grow your circuit, things might become messier to be in the same schematic file, and so you want to export it as a symbol in order to simplify things. To do that, click on the symbol menu here at the toolbar and click make symbol from schematic. Click on that, and do you want to make a symbol view? Okay, that's it. The symbol that we've just created will be named the same as our schematic. Our schematic is currently named untitled-1.schematic.sch. So the symbol will ideally be named untitled-1.sym, shorthand for symbol. And now we just have to look at it, open file, and the schematic is in the FOSS/design, and you will see it untitled1.sch, and this is our symbol untitled1.sym. This is our symbol. To view it, you can just click on the symbol and click OK, and it will open the symbol file. It is a rather simple rectangular. You can edit it, of course, if you want to be more aesthetic, but in our case now it isn't required to be aesthetic, and for the sake of simplicity, let's go ahead. So I want to construct a new test bench right now because I have one already, and the way you construct test bench is essentially the same as you construct a circuit. But there are some things that you might want to consider, because the test bench in particular doesn't need to be fabricatable, or you don't need the test bench to be a real component. So in this case, we just use a generic component supplied by the XSchem. In particular, V's power supply. This is a V supply, and you can find it in the insert symbol menu and the XSchem-library/device, and you just look for V supply, or this is V source. This is a vsource.sym. This is what I use for simulating supply voltage and simulating the signal. And after you choose it, you can click OK, and it will be there. Place it wherever you like, and that's it. It's basically the same as placing any other components, but the most important thing is how do you define the power supply type. Here the V2 is just a simple 3.3 volt supply, while the V1 is a pulse power supply. It represents a pulse signal, and the way it is defined is according to this NGSpice manual book. So you can see here, I just modify the value and insert the pulse signal definition according to the NGSpice manual inside of the value attribute. It is pulse. This is the initial voltage. This is your final voltage. Initial is 0, final is 3.3, and the third 0 here is the delay. We set 0 so because we don't want we don't really want any delay. We don't require any delay whatsoever. And then 0ns and 0, these two 0ns and rise time and fall time. So if you need that, you can fill that, but if you don't need that, you can leave it 0. And 50 ns is the time you spend on V1, and the 100 ns is the total period of your pulse. The number 1 as the last variable is your repetition, like how much pulse do you want it to be there, how many times you want to repeat the pulse, basically that. And after you're done defining it, you can just click OK and it's all set. Also, to act as our probe, we also add some more components called lab bin, and you can find it the same thing as this, in the same way as any other components. Name is lab underscore bin. There you go, and click OK and place it wherever you want and connect some wires to it. Don't forget to change the label name, since it will be the name, it will be the signal name that comes up in the graph. So after we finished setting up the test bench, it's time for us to write the simulation script. Simulation script, as you can see here, is embedded in the code symbol. So in the insert symbol menu, there is a symbol named code and code underscore show. What I use is code underscore shown, because by using the code underscore, by using this code shown, it will also show whatever you write inside this code block. So let's take a look. This is a code shown, but if you use code, it will be something like this. It's just a symbol, and to look at what's inside it, you have to double click it, which is sometimes inconvenient because you might not catch any mistakes that you've made. Like that. This is a code shown. I named it simulation, and it is basically the same as the V source. The only difference is the value will be the spice directive that you want to run. This is the what is it? Oh, yeah, this is a command for the NGSpice to run. And basically what it does here is set the temperature to 85 degrees Celsius. I mean, I just doing some PVD simulation just to know the simulator better. And this is a control block. It tells us to we basically tells the simulator to save all data that has been computed, and then do do a transient simulation with 0.1 nanosecond time step and 100 nanosecond total simulation time. Then we tell the simulator to write the result to inverter_trial_2.raw file, which then will be the database for our graph. And then if for additional demonstration, we can also plot the graph directly using the GUI that present with the current NGSpice. You can just use this syntax plot, and you give the signal that you want to plot. In this case, in and out, to see the difference. And it is ended with NC for closing the control block, and then terminated with end. That's all. That's all from the simulation. The more important code, however, is the models. The models include your transistor models for GF180 MCU, and you can find these code blocks in one of the Testbench that is present in the welcome screen. So here I've opened the test PFET 3.3 volts, and as you can see here, the model's definition are present, so we can just select the script and then copy using Ctrl+C, and then what is my Testbench? Okay, and then paste using Ctrl+V, and there you go, you're done. After you have imported the model definition, just click, oh wait a minute, save the file first so you don't lose any change. Save file, good, and then click netlist. This will generate the netlist that represent your circuit as in the form of spice file. Click netlist, and to make sure that the netlist is according to what we want, we can select the simulation menu and view netlist. Edit netlist. This will bring up the GFIM text editor and all of the netlists that represent your schematic in the Testbench. So this is subcircuit. This is our pin definition, and this is our device. This is XM1, XM2. This is our device. NS to close the subcircuit block, and the global ground. Okay, and that's it. This is our SPICE directive for simulation, and I think all is good right now. So we can just safely close the GFIM and click simulate to begin simulation. Voila! The plot is automatically generated. This is from the plot directive, and you can zoom in and zoom out by right click and highlight or block the region of interest, and it opens the second window, and you can keep zooming until you're satisfied with the result. And there you go, we can see it. The input is a simulated signal, and it's very sharp as a simulation should be. But here you can see the output signal is actually behaving more realistically. It has some kind of rise time and fall time, and it's a little bit wavy, but otherwise it is a very clean signal. We can close it, and we can also close the NGSpice terminal, and there you go. The simulation is done. And how do we add graph like this? To add graph, you can click the simulation menu, and then look at the graph entry here, and choose add waveform graph. It will bring you another graph here, and then to view your signal, just double click here and choose your raw file like that. Sim type is transient. There you go. And you have our and now we have our list of signal that is present in our schematic, and we're only interested in out and in. We'll click that. You can just double click, or you can just edit it in here. Choose out and in, and then might want to change the color. You just hover around the signal that you want to change and click this. There you go. Click apply, click OK, and that's basically what it is. You can zoom using shift scroll, and you can zoom to zoom at each axis. You just hover into the respective axis and do the shift scroll up and scroll down to zoom in and zoom out, and that's it. There you go. Our signal is in view right now. And to zoom it, we can also just right click and block the area of interest like this. That's it. There you go. That's basically how you construct the circuit in XSchem, and how you construct a test bench for it, and how we simulate the circuit. Thank you for watching. I hope you find this helpful, and sorry if you have any difficulties understanding, because this is my first time creating a tutorial. Thank you for watching, and see you.